Alright, now let's go ahead try to understand what is regularization. Let's say if we don't use regularization, then what happens? As we have been already discussing about what happens if we don't use regularization in our previous lesson, it actually simply overfits our model. For example, if you consider this algorithm here, this actually figure here, in this figure what you get here? You get the validation data loss. Alright, so this validation data loss is more than this training data as we increase the iteration, and the separation distance becomes larger as we train our data set. As we increase the number of iteration in our data set. So ultimately what happens, when you get high loss for validation data, that's mean the low validation accuracy for the low validation accuracy. So in this way what happened, your algorithm is so trained on the training data set and it is not generalized. Not generalized means your algorithm might not perform well on the unseen data like validation data and the test data. Our ultimate goal is to produce a high accuracy in validation data and the test data. Sometimes what happens, we don't get a good accuracy in the training data, even though we can use our algorithm if it is getting better accuracy in validation and the testing. That's mean it is known as underfitting. Alright, so in underfitting case, if you don't train your model for further iteration, even though you can use without any problem. But if you use in overfit case, then ultimately you will be getting more error, and that's the problem here. So the regularization avoids this overfitting, and this generalized curve actually your model, a machine learning model, and ultimately it prevents the overfitting. There are many types of the regularization like L1 and the L2 regularization. We are going to discuss here first L2 regularization. Instead of just loss minimization, which we actually see in our general algorithms without regularization, we will now minimize loss plus complexity, which is called structural risk minimization. It's like, in general, if we don't talk about the regularization, we decrease the loss of the model only, but during the regularization, we will try to keep the balance between the loss of a model as well as the complexity of the model. Our training optimization algorithm is now function of two terms: the loss term, which measures how well the model fits the data, and regularization term, which measures model complexity. You can think the model complexity in the two ways. Model complexity as a function of weights of all the features in the model, and model complexity as a function of the total number of features with non-zero weights. Alright, so as we increase the complexity of machine learning model, number of features and the weights of the feature increases, ultimately that might produce a more variance. L2 regularization, that is where prevents the overfitting. If a model complexity is a function of weights, a feature weight with a high absolute value is more complex than a feature weights with low absolute values. L2 regularization can be represented with this formula. It is a sum of weights square values. For example, let's say if Wn is high, that means the impact of this Wn will be very high, and that is what we try to prevent here. So in L2 regularization, we try to prevent here high weight. So we try to reduce overall weights and we try to keep all the machine learning model weights or feature weights close to zero, as close to possible. We can quantify complexity using the L2 regularization formula, which defines the regularization term as sum of a square of all the feature weights, Alright. So weights close to zero have a little effect on the model complexity, while outlier weights can have a huge impact. You can simply understand that, let's say if these weights are 1 and the 1, then the 1 square 1 is 1 and 1 square 1 is 1. This is simply just a 2. But let's say if this weight is 10, then the square is going to be 100. So this is going to have a huge impact, and that is what our main purpose, to reduce the weight. Alright. So how we reduce the weight? So we do it with the regularization, and there is another term, regularization rate, which control how much regularization we are going to do. Earlier we had seen the formula for our regularization as a loss term plus this complexity of the model. So there we get this complexity of model multiplied by this lambda. So this lambda is known as a regularization rate. Increasing the lambda value strengthens the regularization effect, and this brings our model weights close to zero. But do remember, it is not going to equal to zero, but it try to as close as possible. You have to choose your L2 regularization very carefully. While choosing the lambda value, the goal is to strike the right balance between the simplicity and training data fit. Because if we increase regularization on the model too high, then our algorithm might not fit well. That means it might end up underfitted. If your lambda value is too high, your model will be simple, but you run the risk of underfitting your data. Your model won't learn enough about the training data to make useful prediction. If your lambda value is too low, your model will be more complex and you run the risk of overfitting your data. Your model will learn too much about the particularities of the training data and won't be able to generalize the new data. So these are some tricks which we have to pay attention while choosing L2 regularization and its regularization rate. Alright, perfect. So this is all about in this lesson. Thanks a lot for watching it. I'll see you in next lesson.